Everyone, my name is Rohit Kumar Singh and I'm the teaching assistant for the course Wave Optics, and this is fifth live session where we discuss few concepts, recap some topics and then solve examples based on them in order to help you with the tutorial assignments. So last week we discussed interference by thin film and concept of Newton rings. So there's one more topic similar to that, which is called Michelson interferometer. Okay, so we'll discuss that today and then try to solve some problems based on that. Before we start, do you have any question or doubt from last week or something that you want to discuss?
No, sir.
No, sir.
Okay, thank you. Okay, so then let's start. So yeah, last week what we saw is if you have a plain parallel film and it is being illuminated by plane waves like this, then the condition that we got for minima and maxima was basically so the path length, path difference. So if the refractive index of this material inside the two parallel film is n, then the condition that we obtained was this, right? And this theta is this theta is basically angle of refraction. Okay. So this was for minima, and for maxima we have m plus 1 to m plus 1 plus m plus half. So these things we discussed last time. Now there is one very interesting device called Michelson interferometer. So this is its concept is not it's very similar to what we have discussed, like Newton rings and all, but this is a very important device. It is used in various fields, like, so the most important discovery made by using this kind of interferometer is you guys have heard of this LIGO experiment. Have you heard of this LIGO experiment?
No, sir.
No, sir.
So it's its full form is basically observation of gravitational waves using large interferometry or something like that. I forgot exact full form, but so there what they discovered is so something called gravitational waves. Do you know what gravitational waves are? So
Yes, sir.
yeah, so gravitational waves are basically disturbance in space-time of the universe. Like we know that we live in a flat space-time, and whenever there is a mass, the space-time gets curved. So this is a flat space-time. So if there is no mass, our space-time is flat, and special relativity is applicable. But whenever you have a mass, like sun or any other mass, the space-time gets curved. Okay, so you have this curving of space-time. And if this mass is now, uh, if there is a change in the configuration of this mass, or something, abruptly something is happening, like if a star destroys, like uh, the star goes supernova, then the mass disappears quickly, then this curved space-time, retracts. And so think of it like a disturbance, okay, happening in the space-time, and then it propagates in the space-time like a wave, and that wave is called gravitational wave. And we have discovered that gravitational wave in LIGO using this kind of interferometry, Michelson interferometry. So this is very interesting. So okay, so let's first discuss what exactly Michelson interferometer is. It's a very simple device. I mean, it's a tabletop experiment basically that you can do in your lab, but it can be scaled to a very large, large area and large lengths. So that's what LIGO does. So let me explain what on the tabletop, what does it look like. So you have a suppose you have a point source, and then you can have a glass plate like this. So to get a extended light source, let's call the middle point P. And so suppose there is a light ray coming from this source like this. Okay, here you keep a glass, so this is a silvered glass mirror. So what it does is it partially transmits and partially reflect the incoming light. Okay, so then what will happen is some light transmits through it, and some gets reflected like this. Okay, let me okay, and you have a mirror here, let's call it M1, and you have another mirror here, let's call it M2. Okay, now both light, so this light gets reflected from this M2 mirror. Okay, and then it again gets reflected through this silvered mirror here, half silvered mirror, and this light that is going towards mirror M1, it also get reflected like this, and let's say it transmits through this half silvered mirror, and here you are observing. So this is okay, and let's call this distance x1, and so this distance x2. Now what you will see here is that so two light rays coming at you, right? And so this light ray that is getting reflected from M2, it will appear to be coming from this place, right? So let's call it M2 prime. Let's mark it with dashed lines. Okay, and its distance will be x2, right? The same distance that it has from G1 to M2. So in general, no, what you get here is that a scenario similar to this thin film uh, scenario, right? You have two sources of light separated by a
Excuse,
disk.
excuse me, sir.
Yeah.
I have one doubt that I have read in book that they imagine that M2 dash is the image of M2 and thin film produced between M1 and M2 dash.
Sorry.
Am I
M2 is a
audible?
yeah. So that's okay. In thin film, what happens is
I am also in teaching profession, so it is very difficult to clear the students that M2 dash. In book they said that M2 dash is image of M2,
yeah. It is image of M2. Yeah, that is fine.
and here you are explaining that these rays appear to come from M2 dash. So M2 dash
Yeah. It's
is
similar thing. So you see, uh, okay. Appear to be coming means so. What matters is when you are looking from here, okay, you will see two source of lights, right?
yes.
Okay, so one source is this M1 and other source is M2, right? But M2 can't be, I mean, M2 is here, right? So how does it,
Yeah.
how are you looking at it here? Because see, the light is getting reflected. So that's why it is making a mirror, I mean, it's making a virtual image of this mirror at distance x2 from this G1 glass plate, right? So yeah, you can say that the mirror it is a sorry, it's a virtual image of M2 prime. That is fine.
And no description about something image of M1.
No,
They
no.
describe image of M2.
M1. Yeah. I mean, if you look at this same device from here, okay, then
Yeah.
you will see the image of M1 forming somewhere here, right? M1 prime. But that is a perspective difference, right?
Okay.
Because so to get interference, no, this distance will be too large. If you are looking from here, you won't get any interference because this distance is too large, right? And the light might not be coherent, or it goes out of phase in that distance, so you won't observe the interference pattern. But when you are looking from here, then this distance is small, and this distance you can control. So M1 is movable, okay, so you can move it.
M2 is stationary.
Yeah, so you can move it, and you can control this distance to
And I think this is also known as Hedinger fringes.
yeah. Okay. Now, okay, so let me so the condition of thin film will apply here. So, and since there is no medium, so we'll keep n equal to 1. So it will be just from this formula, it will be just cos theta equal to m lambda. Now, what is theta here? Can you guess?
Angle of reflection, inclination.
So yeah, that is true. Uh, so yeah, to understand that, okay, so first of all, this is a very simplistic picture, okay, just to convey you that, okay, this is a thin film condition that we are getting here. But in realistic cases, what happens is that this is because of this point source. What you get is, so let me draw the picture that you see in all the books. So now this is your first mirror M1, and so there is a second mirror M2, okay, and they are separated by distance d. So this one is your basically M2 prime, okay, and you are looking perpendicularly from here. Okay, and so light is basically, so you have an extended source of light. So let's imagine, because this is a plate, so let's imagine a light ray going from here, okay, and reflecting and coming at your eye like this. Similarly, this one will go here, and it is coming to your eye like this. And if you extrapolate it backwards, you will see that this the image of, I mean, this object, the image of this object is forming somewhere here. So let's call it P1 due to the M1, and then due to the M2, if you extrapolate here, it's P2, and the distance between them will be 2D, right? Because the light is traveling D upwards and D backwards, so 2D will be the distance between the images. And this angle, so if you consider the center point, sorry, yeah, so this angle is your theta, okay. Which is which you can say that in this case it was the angle of, you know, this angle refraction. Here also similarly you have this angle, so that's why this theta is there. And what you will get is concentric fringes like you had in Newton's rings experiment. Okay, if you have a point source like this, and you are using a glass plate, so this is your point P here. Okay, do you get it? So this is the realistic scenario. Okay, this one was a schematic diagram, but this is the realistic scenario that you have. Okay. Now, okay, so then this is the condition for minima from our thin film formula, and for maxima we have m plus half lambda.
But sir, here I think take the condition in refracted region. These are the conditions for transmitted region. But in Michelson interferometer, we are taking the condition in refracted region. Sorry, transmitted region. Sorry, transmitted.
Yeah. Here the angle of
2D
transmission, and
positive.
so because this medium here is same as the medium here, so angle of transmission and angle of reflection will be same, right? There is no deviation in this medium, in the gap between M1 and M2. You understand?
Okay.
So the angle of transmission is the angle of refraction here. The formula won't change. If there is if you introduce a medium between M1 and M2, then there will be a deviation, and the angle of you have to consider the angle of refraction. So it is not exactly like the thin film case, because here we have considered, you know, this thin film to be made of a glass or some different material. Here the both the medium between the two interfaces is same as the medium above the interface. So it's so that's why the angle is angle of transmission is same as the angle of refraction. So that's why this theta would be just this angle. Okay. So this is the condition for minima and maxima, because you have this phi phase difference that happening here at the glass plate. Now if you look at this formula closely, so you have I mean, for the maxima, theta is cos inverse of m plus half lambda divided by 2d, right? So just from here, this is all in same bracket. So what you see is from here is that if you reduce the distance between the two mirrors, so reducing d, what will happen is fringes will appear to collapse, right, at the center. So because if you are reducing d, that means theta will increase, right, for a particular for a particular mth order of fringe. So the fringes will be appear to be collapsing. You have to imagine it little bit. Can you imagine it? So for an example, you can take some lambda. So this is a one standard example I am taking. So let's say you have lambda 6 into 10 to the minus 5 centimeter, and this distance between the two mirror is suppose 0.3 mm. Okay. Then if you calculate theta, it will be cos inverse of, so m divided by 1000. Okay. And this will correspond to, for different m, this will correspond to 0, 2.56 degrees, 3.62 degree, 4.44 degree, and 5.13 degree, and so on. And so corresponding m is, so m will be 1000, 999, 998, and so on. Okay. So you see the first, this is the central bright fringe at 0 degree has the order 1000. Okay. Then the next one is has the order 999, and its angular distance is 2.56 degrees. Okay. Now when you decrease the distance, so when you decrease the distance to half, so like 0.15 mm, then what happens is that if you calculate theta from this formula, you will get this. Okay. And this for different m will be equal to 0 degree, 3.62, 5.13 degree. Now you see the difference. You are skipping one angle. Okay. This angle is gone. Now this angle is gone. Okay. And so for m you will get 500 here, 499 here, 498 here, and so on. Okay. So first thing you notice is that the angular separation between the fringes is increasing. Okay. So separation increasing. Okay. They are becoming less closely spaced, right? and the number of fringes that you were number of fringes that you were getting earlier is now getting lesser and lesser, so they are collapsing at the center. So this you can check it mathematically also like this. So yeah, it's a very nice experiment that you can do on tabletop. You can decrease the distance and increase the distance to check whether the fringes collapse or emerge from the center. And so mathematically you can understand it by this formula basically. Now for the central fringe here, theta is 0, so cos theta is 1. We can write just 2d is equal to m lambda for the case of minima. Okay, and if now when you change the distance, so suppose now you move m1 by a distance d naught, okay, and n fringes collapsed, so then you get so basically you get this, right? Sorry. Yeah, this is fine. And you can subtract the two equation to get this. And then from these two equation you get this condition, you get this formula for wavelength. So just by changing the distance of the between the two mirrors, you can check how many fringes are collapsing, that you can measure, and from there you can calculate the wavelength of the light. So it's a very nice experiment that you can do. So similarly in Newton's ring we can calculate the wavelength of the light by looking at how many fringes are appearing or disappearing. Similarly here also you can calculate the wavelength of light by looking at the number of fringes that are collapsing. Is this okay? So we'll see some examples on this formula. Now what happens if you have two wavelengths? So suppose you have a sodium lamp with two different wavelengths, light of two different wavelengths emitting from it, lambda 1 and lambda 2. Okay. Then so then if two d by lambda 1 subtracted by 2d by lambda 2 is equal to half, okay, and if this condition is met for say lambda 1, okay. So if these two condition is there, then what will happen is I mean if you solve these two equation, you will get 2d sorry cos theta equal to m plus half lambda 2. Now what does it lead to? Can you guess? So this is the condition for minima and this is the condition for maxima, right? And both are simultaneously happening for both different light wavelength of different light lambda 1 and lambda 2. So what will happen is that all the fringes will disappear. Like where you have dark fringes from lambda 1, you will have bright fringes from lambda 2, right? And they will overlap and they will disappear. So you will get the photographic plate that you will have no fringes, okay. All fringes disappear basically. And then if you move your mirror by little bit more and if you get a condition like this, then they will reappear. The fringes will basically reappears. Because for this both will have either maxima or minima coinciding. Do you understand it? Yeah, okay, thank you. So and in general this is so in general if you keep changing d such that you are getting half, then 3/2, then 5/2, all of them will lead to this condition of no fringes, okay. And then if you have if the difference is integral like 1, 2, 3, then they will appear. So there will be a disappearance and appearance of fringes. So you can this experiment is also very nice. You can use a sodium lamp which has 2 lines, and you can check this using Michelson interferometer. Okay, so yeah, that is all for the Michelson interferometer. So do you have any question or doubt?
So this 2d by lambda 1, or it is given, or
yeah
2d by lambda 2?
Yeah, so this condition has to be satisfied, okay. And how can you get this condition? You can get this condition by changing your d distance. You can change. Lambda 1 and lambda 2 are fixed, right? Only the distance
And
between
in bracket,
sorry,
and the bracket given, that is given in problem, or we are
no, so
2D.
problem we will see, okay. But this condition has to be satisfied, and then for lambda 1, if you have the minima case, automatically for lambda 2 you will have the maxima case, and then the fringes will disappear. So these two condition has to be satisfied. Okay, problems we will see how the problems on this concept will be there. So we will see one example, but the concept you understand, right? So you change, so you get a source of light which has two wavelengths, and by changing the distance between the m1 and m2 you get this condition satisfied, and then you have this condition for minima, right? So once you get these two conditions satisfied, then automatically for lambda 2 this condition will be satisfied, because when you solve these two equation you get this for lambda 2, right? And then the fringes will disappear. So it is just a matter of, in experiment what you will do is you will just control the distance between the two mirrors. If you change do very carefully, slightly changing, you will see that the fringes will there will be a distance for which no fringes will be observed. Then you are sure that all these conditions have satisfied, and then you again start increasing the distance, then again they will reappear. Okay, because then you get to this condition, and then again they will disappear, reappear. That will keep happening. So that is the concept. Now problems we will see how the problem on this concept will come, but yeah, this is the concept. Is that okay?
Okay, sir.
Okay, thank you. Okay, so let's now move to some problems. So yeah, this is the first problem. So in a Michelson interferometer, one sees a dark central disk surrounded by concentric bright and dark rings. Okay, so yeah, in the center you have one dark disk, and then there are bright and dark fringes like this. Okay, now one arm of the device is 2 centimeter longer than the other. So it is talking about this x1 and x2. Okay, so it's basically telling you that okay, the distance between both is 2 centimeter, d is 2 centimeter, and the wavelength is given. So lambda is 500 nanometer. This is given. Then question is the order of 6th dark ring from the center is. Okay, so 6th dark ring means so this is 3rd, 4th, 5th and 6th. So what will be the order of this? So you have to find m. Okay, so it's a simple problem. Now okay, we have this condition of maxima, or we can use the minima condition, but anyone is fine. Right? Yeah. Oh, sorry. No. We have to use the minima condition, right? M lambda. So, yeah. For the center, cos theta will be 0. Cos theta will be 1. So you have just 2d equal to m lambda, right? So for the center, you can calculate the order, which is m equal to 2d by lambda. 2d means 4 centimeter and lambda is 500 nanometer. So let's convert it into SI units. 4 into 10 to the minus 2 divided by 500 into 10 to the power minus 9. So what will be the value? 4 by 5 8 into 10 to the power, so this is 10 to the power 7, 10 to the power 5, right? So it is 80,000, correct? Now, but this is the order of the uh, central dark ring, right? Yeah. So you have to go back. You have to go to the sixth dark ring. So you have to just yeah. So as we discussed here, the order get decreasing as you go to higher angle. Okay, so just you have to subtract 6 from it. So yeah, C will be the correct answer. Okay, so this one was easy problem. Is this okay? Okay, let's go to the next problem. Here in the Michelson interferometer, if one of the mirror is moved by a distance 0.08 mm, 250 fringes crosses the field of view. The wavelength is. This one is also very similar, straightforward, based on that formula, right? So yeah, what is the formula? So basically lambda is 2d by n, right? 2d naught by n. D naught is the distance moved. So 2 into in meters, it will be 8 to the power 10, 8 into 10 to the power minus 5 meter. 250 fringes moving. So you can write it like this. So and then it will be 6.4 into 7. So 640 nanometer. This is straightforward. It's fine, right? Okay, thank you. So yeah, the problems on these things, like last week we also saw Newton's rings. The problems are not very calculative, or you don't need much calculation. You have to just understand what the problem is telling you, and you have to use the appropriate formula, which are, the formulas are also very simple and small, but sometimes the question that will be given to you will be twisted in such a way that you will get confused, so you have to just understand it properly. So let's do this. So this is one problem on two wavelengths. So okay, now you see so this is how the problem will be stated on this concept. So the Michelson interfero experiment is performed with a source consisting of two wavelengths. So lambda 1 and lambda 2 is given. Lambda 1 and lambda 2. The distance the mirror has to be moved between two positions of the disappearance of the fringes will be. Now, as I said, so what we have control over is the distance between the mirrors, right? That we have to move to see the disappearance of the fringes, right? Now how do you how can you calculate it? So what is the condition for the disappearance of the fringes? 2d by lambda 1 minus 2d by lambda 2 is equal to half, right? So you can just just But wait. So uh, so this is the condition after which you can see the disappearance of the fringes. Uh, but this distance d is not the distance that you are moving, right? So suppose earlier you had the original distance was d, and now you have moved your mirror so that so that the distance d is now d minus d naught. So this delta d is basically d naught, right? So yeah, so then you put this here, okay, and yeah. mm, wait, no, something is, so the distance, the original distance is not given, right? um, oh, but wait, we don't need the origin, we want to just calculate the delta d, right? The mirror is distance, yeah, it is asking the distance, I mean the difference of the distance, right? It is not asking d naught. So I think it's fine, we can just use this formula. Okay, let's see if we calculate what we get. So lambda 1, lambda 2, and then you have delta d, 2 lambda 2 minus, sorry, 2 is also lambda 2 minus lambda 1 equal to half, or you have d equal to lambda 1 lambda 2 divided by 4 lambda 2 minus lambda 1. Okay, what do you get? So sorry, lambda 1 into lambda 2, 488.6, 488.2 is 238.534, something like this, and the difference is very small, 0.4 nanometer. Okay, and yeah, if you solve it you will get something like this, close to this. So it's 0.298 nanometer. Okay, so this is the distance that you have to move the mirror. Yeah. Is this okay?
Sir, but you like in the formula, the D is, it is not D not in the formula, right?
No, no. This form, this one?
Yes, sir. Yeah. Yes, sir.
Yeah. This is D. I mean, this is the distance. Okay. Now what I am doing is, so earlier suppose you had D, and then when you move the mirror, you get D minus D naught. Okay.
Yes, sir.
So, and wait. Mm, and then you're okay, understand. Oh, sorry, yeah, this one will be 0, right? Because mm, if you subtract,
Sir, this may be D plus D naught also. We are increasing or decreasing both ways possible. So D plus D naught be possible hai.
no, let me think. So,
Because in formula
Yeah,
T,
yeah.
they are taking plus minus.
yeah. Uh, so, when you, so, okay. So, to go from half to 3 by 2, okay, or go from, to go from half to 3 by 2, what you have to do, do you have to increase the D or decrease the D? So if lambda is greater than lambda 2, lambda 1 is greater than lambda 2, right? And so the numerator is fixed, right? Then okay, if you increase the D, so suppose D becomes 2D, then okay. So if lambda 1 is greater than lambda 2, then you have to so to balance it, you have to decrease the distance, right, to get to 3 by 2, and opposite thing happens. So if lambda 1 is less than lambda 2, you have to increase the D. Okay, so that's how you can you can put minus and plus here. So you see here, if you are considering lambda 1 to be your lower wavelength, like this is 488.2 and lambda 2 is 488.6, right? Then what you have to do is you have to increase the distance, right? So this will be a plus sign. You are right. Okay, now so this formula, okay, this formula this is a general formula, but this is what I mean, we need. So this is what we need for the disappearance of the fringes, right? Along with this condition that 2d cos theta is equal to m lambda. Sorry, m lambda 1. Okay, but this is the condition we need. And earlier, suppose we had d distance, we move to d plus d naught distance. At d distance, we don't know that. Actually, it is very misleading. So suppose earlier we had d1 distance, not d. Okay. Earlier we had d1 distance, where the fringes were not, fringes were clearly visible. Okay. And when you move to d1 plus d naught distance, so this is d1 plus d naught distance, the fringes disappeared.
So should we equate it with 1 first and then with half? We'll minus the two distances. So we'll get how the fringes will appear first, but then they disappear.
Yeah. So that's what I'm saying. So, yeah. So the question is the distance the mirror has to be moved between two positions of disappearance of the fringes. So that's why there will be one for d1, right? Half. This will be one condition, and then when you move to d1 plus d naught, you have another condition, and then you subtract these two. Okay, and what you get is 2d naught by lambda 1. 2d, fine, minus 2d naught by lambda 2 equal to 0, right? No. Yeah, that is why I'm getting confused. Wait. I thought it was straightforward, but it is not. Wait. Let us think. So this is one condition. Okay, at d1 you had disappearance of fringes. Oh, I see. Sorry. I'm stupid. So when we are increasing the distance, the next disappearance will happen at 3/2, right? Not at half. So now you understand what happened. Sorry, I was being stupid. So now you subtract. So this is equation 1 and equation 2. Now you subtract, what you get is 2d naught by lambda 1 minus 2d naught by lambda 2 equal to 1. Yeah, that's why I was because I know that there should be this 4 should be 2. Okay, that's why I was confused when the factor 4 was there. But no, okay, no, we I think we got it. Okay, so this we have to solve basically. So now the d naught will be simply lambda 1 by lambda 2 and 2 lambda 2 minus lambda 1. If you solve it, you will get this value. Should be millimeter, in millimeter. Yeah, any doubt? Now it's clear, right? So the mistake that we were making is that we were putting half at both the places, because the next order will disappear when the distance between them will be 3/2, not half, right? Is this okay now? Yeah, okay, thank you. Yeah, so yeah, this one was also easy. Just we made the silly mistake here. Okay, good. Yeah, I didn't solve it earlier before the class. I thought this will be a straightforward, but yeah, it was little tricky, but it's fine. So this way you have to understand what the problem is saying. Okay, nice. Let's move to our next problem. Okay, now this one is straightforward basically. So in the Michelson interferometer, calculate the various values of theta prime. Distance between the mirrors is given. So it is 5 into 10 to the power minus 3 centimeter. And you have to show that if d is decreased to this, so now the new d prime is 4.997 into 10 to the power minus 3 centimeter. So it is decreased by a very a small amount, right? So what is the delta d? It is 0.003 into 10 to the power minus 3 centimeter, correct? So this is a very small distance, and yeah, and the problem is for this change of distance, 200 fringes are disappearing. So we discussed here, right? When we reduce the distance between the mirrors, fringes collapse, right? There will be a collapse of fringes, and so that's what is happening here. So 200 fringes are collapsing. So
Sir,
yeah,
they are not saying 200 fringes are collapsing. Just one, the fringe corresponding to m is equals to 200 disappears.
okay, yeah, you're right. This is order. This is talking about the order, right? Yeah. Okay, so that means the central fringe should have the order 200, right? Because fringes collapse in the center, so this should be the central fringe. But we can check that, I think. No, because then the theta prime would be just 0, right? If this is the central fringe. So no, this cannot be correct. Okay, we can calculate it. Lambda is given 5 into 10 to the power minus 5 centimeter. Okay. So yeah, we have this formula of minima. Okay. And we can find theta like this. Now, so you know that for cos, like this, I mean a real solution for this equation will exist only if this varies from 0 to 1, right? So m lambda by 2d should be from 0 to 1, right? So maximum m that can be there would be 2d by lambda, right? And d is given here and lambda is also given, so we can calculate that. So Yeah. So then cos theta is equal to basically m lambda by 2d. So m equal to, so yeah, you can so this, if you calculate, or better you can calculate lambda by 2d, 5 into 10 to the power minus 5 divided by 2 into 5 into 10 to the minus 3, it will be 0.005. So 0.005. Okay. And yeah, and so the maximum, this one is like, if you invert it, it will be 200. Okay, so this is the maximum order, right? So this, oh, okay, so 200 is the maximum, I mean the largest order fringe, you see. So that means the fringes are basically appearing, it's not collapsing, they are basically appearing, seems, right? Because that, then the 200 one is disappearing. So it's not collapsing, it is expanding. No?
Yes, sir.
So yeah, I mean theta you can calculate simply from here. So cos theta will be just 200 into 0.05, which is just 1. Oh, so then the theta is 0, which I guessed right. Wait, what is happening? Wait. Okay, now if we take d is equal to 4.997 into 10 to the power minus 3 centimeter, and if you calculate the lambda, so now it's d prime, lambda by 2d prime, 4 into 10 to the power minus 5 divided by 2 into 4.997 into, let me use the calculator. So this is 5 pi 99.4. So 10 to the power minus 3, get cancel, you have 10 to the minus 2. I think, okay, so this is 0.005. Approximately this will be the value. But I mean, you have to go little, okay, so we can keep it like till this, okay. And if you then calculate m prime, so just 1 by this thing, so let me do that. It comes about 199.888 of this. So yeah, but the order can be only integer, so I think this will be the acceptable order for this. Right? And then theta prime you can calculate. So basically cos theta prime will be 199 into 0.005003. This should be 0.9955. Then theta, you can just take inverse of this, Uh, so 5.38 degree, something like this. Okay, top prime.
Sir, if this type of problem will be coming in main examination, then how can we calculate so fast in limited time? Calculator is not allowed.
No, no, I don't think this type of. So this is from a book, not from the. So this problem I kept it to just showcase how to showcase the concept that we discussed here, basically. Okay. So let me just don't worry about this type of problem coming in exam. Obviously, the if you don't have calculator, then the problem will be such that you don't need calculator. So don't worry about that.
Okay, sir, one personal question is also I want to ask.
Okay.
Due to some problem out of station, I missed the one assignment.
Oh,
So,
okay.
is there any problem for main examination?
Uh, I think for one assignment there should be no because the some percentage of marks is uh, given due to assignments, right? Like
Yeah,
examination
30.
has 60% weightage, and then assignment have 40, right?
Yes, yes.
So yeah, then if you have 12 assignments, one assignment worth of 40 by 12. So yeah, then I think that mark will be deducted.
Okay, but 11, if I will done 11,
Yeah,
I will perform
yeah,
11, no problem. I
no
mean,
problem, no problem.
I will appear in main exam, na? No hurdle.
Yeah. Even if you don't submit any of the assignment, I think then also you can appear, but then you won't be able to, you know, get much marks.
Sir, I think 8 out of 12 are considered best 8.
Oh, is that
Uh,
the case?
I read somewhere on the site, I don't remember properly.
Yeah, I also remember something like that. Oh, then it's fine then. Like, if you missed
Okay.
one, then you have 11. So eight will be the best. 8 will be considered. So I think
Okay,
that is
thank
fine
you, sir.
then. Okay, so now what happened here is that when we reduce the distance, uh, earlier we our our yeah fringe corresponding to order 200 was at 0 degree, uh, but when we reduce the distance, now it is at 5.38 degree. Okay. Yeah, I think that is what we expect, right? Decreasing the distance, increase the distance between the two fringes. Sorry, also I think this one, the order should be the same, right? Order will be 200 because 199.88 should round off to 200. Yeah, so now the 200 order fringe is at 5.38 degree. Mm, but I don't know why this information was given, that the m equal to 200 is disappearing.
Sir, M is equals to 200, that one fringe is disappearing means it was a bright fringe, right?
Okay. Oh, okay.
So
Wait,
yes,
wait, wait, wait,
I'm
wait. Calculate the various values of theta corresponding to bright rings. Ah, yeah. Sorry. Again, I made a mistake. That's why. Okay, so and I took here the condition for the dark fringes, right? So that's why I think, yeah, you're right, yeah, sorry. Mhm. Okay, I missed this part. You guys should have pointed out. Okay, yeah, if you have to take this formula, not this.
Sir, but this is the condition of dark because all mathematical conditions are taken transmitted region.
Sorry. No.
So
So
we,
here it is written that uh, calculate the various values of theta prime corresponding to bright ranges for bright rings. Okay, corresponding to bright rings for d equal to this. So first we
but sir,
had to we had to calculate simply the cos theta m plus half lambda by 2d. Okay. So
so this is the condition of dark in Michelson.
no. This is for bright.
But sir, they are taking transmitted region. Reflected are बिल्कुल just opposite to transmitted conditions.
No, where
What I have
this
read.
is reflect. We are talking about the reflected part, right? Here we talked about the after reflection.
No, but sir, telescope in Michelson, we are taking transmitted region, not reflected region.
No. We whatever we have discussed till now, it is the reflected from the reflected part. We are not discussing the transmitted region. So
Okay.
this angle. So if you remember the thin film case, this angle is the refracted or transmitted, but what happens is that after this light comes here, it gets reflected, and we are looking at the interference of these two, right? So we are looking from above, not from below. And when this is the condition, then these two formulas are valid. Here also you see this, we are observing from here, not from here. So you can go and check the thin film case, okay? Then I think it will be clear. So yeah, I think C is correct. So we should use this formula, and yeah. So then from there you can do the same calculation basically. I think you will get to the correct answer. I don't want to do it again. Yeah, this is fine. Okay, yeah. So then what basically happens is that uh, decreasing this distance from 5 into 10 to the minus 3 to 4.997, the 200 m equal to 200 order fringe will disappear. So what remains is the 199th order, and you have lambda, you have been given theta prime. You can calculate using this formula. So basically just put 199 here. D is also given to you, right? So you can just do a simple calculation and calculate it. So that's why this information was given, right? So I did not see this condition, that's why I got confused and I went to a different direction. But this is straightforward problem. There's no need to do all this. Okay, so any other question? So this was actually the last problem for today. So we have to discuss one topic, Fabry-Perot interferometer, that I thought that we will not have time today to discuss. So that's what we can discuss next week. Okay, so yeah, let's do that. Okay, so any question for today?
No, sir.
Okay, so thank you. Okay, thank you for joining. Let's meet next week. Bye.